Recording. Sets of numbers. The first set of numbers is a set of natural numbers or counting numbers. Long ago, it was natural to count physical objects with our counting fingers. So we use the letter, what looks like a capital N for the set of natural numbers. And that includes the set, using curly braces for the set notation, 1, 2, 3. So a pattern is established, then we show ellipsis to mean that the pattern continues, and then close set. So this set does not include 0, but when we include 0 with the set of natural numbers, then we have the set of whole numbers represented by capital W. So this is the set 0 union, kind of means together with the set of natural numbers. So now we have the set that contains 0, and we establish the pattern again, ellipsis, and this is the set of whole numbers. The set of integers is the set of whole numbers together with their, or union, their opposites. So the letter Z, Z for Zahlen, that's a German word, is all of the opposites. So opposite of 3, opposite of 2, opposite of 1, and then all the whole numbers forms the set of integers. The set of rational numbers is a set of all numbers that can be written as a ratio or as a quotient Q. So we're going to use the letter Q. Q is chosen for quotient. So this is the set of all numbers that can be written as a quotient or a ratio A divided by B, where A and B are integers, where A and B, and soon I'm going to define the next symbol, which means is an element of, or is a member of the set of integers. So A and B are elements in the set of integers, set Z, but one restriction, the denominator B cannot be 0, since division by 0 is undefined. Any number that cannot be expressed as a ratio of integers, A divided by B, is not a rational number and is therefore an irrational number. And the set of irrational numbers is represented by Q with a bar on top. The bar means not, so not rational. And examples are pi, that's the lowercase p in the Greek alphabet, pi, which is approximately 3.14159. Its decimal never repeats and never terminates, which is true for all irrational numbers. Their decimal expansion has no repeating pattern and never terminates. Another example is Euler's number, named for Leonard Euler. It's a lowercase e, and the value is approximately 2.718. Decimal never repeats and never ends. The set of real numbers is represented by the set R, and it's all the ordinary numbers, whole numbers, fractions, decimals, repeating decimals, and is the union of the set of rationals together with the set of irrational numbers. So it's the union of rational numbers, union, irrationals, Q bar. So in the rectangle below, if we imagine separating this box into two subsets, on the left will be the set of real numbers. And real numbers can be thought of as being divided into two subsets further. So we have rational numbers. Those are all the natural numbers, integers, fractions, and numbers that are not rational or members of the set Q bar. So the union of rational numbers with irrational numbers forms a set of real numbers. And then we get to the definitions that allow us to create imaginary numbers. So one definition is that the square root of -1 is undefined in the set R, set of real numbers, but is defined as the imaginary unit in the set of imaginary numbers. And a second definition is that I squared equals -1. So again, I, the imaginary unit, is the square root of -1, and I squared is equal to -1. Now, complex numbers is the set represented by capital C, and a complex number in complex form is the sum of a real number, A, so A is taken from set R, and B is also taken from the set of real numbers, so they're elements in set R. And a complex number is written as A plus B times I, and A plus BI is said to be a number written in complex form. Now, I mentioned the symbol that looks like an E, which means is an element of a certain set. So for example, -3 is an element of the set of integers, or is a member of the set of integers. So we can use the symbol as an element of the set Z. If a number is not a member of a set, then we use the symbol that means is not a member of a set or is not an element of a certain set. For example, the number 0 is a whole number, but 0 is not a natural number. So 0 is not an element of the set of natural numbers. The next symbol means proper subset. So we have two sets. Say first set is 1, 2, and a second set contains 1, 2, and 3. So every element of the first set on the left, 1 and 2, every one of its elements is contained in the other set on the right, 1, 2, 3. And there is the element 3 in the second set that's not in the first set. So the first set, there is no element in the first set that you cannot find in the second set. So set 1, 2 is a proper subset. Every element is contained in the other set. Additionally, there is at least another element in the set on the right. Whereas, if we include the element 3 in the first set, now every element of the first set is contained in the second set, and they have the same elements. So in a sense, they're equal. So that's why we have what looks like an equals bar. And we'll call this symbol subset. So the set 1, 2, 3 is a subset of the set 1, 2, 3. And furthermore, they're equal because they have the same elements. The next problem is kind of like a translation. To translate the set of all x, there's a vertical bar that means such that x is an element of the set of positive integers. So this means the set of all x, and again, the vertical bar means such that, and then there's a description of the variable x is a positive integer. So the set of positive integers includes 1, 2, 3, ellipsis. That can be expressed as the set of all x, such that x is an element of the set z plus. Some exercises. Number 1, convert 5, 6 to a decimal. So we have to use division, divide numerator, or dividend 5 by 6. The number on top goes inside the box, top in the box. We need a decimal point and at least one zero. 6 divides 50. Remainder of 2. Bring down a 0. 6 divides 20. Remainder of 2. We may have a repeating pattern here. And to show a repeating pattern, we have to show it 3 times. So there it is, third time. So 5, 6 is exactly 0.8333 ellipsis, or we can put a bar on top of the repeating digit, the repetend, 0.83 bar. A dieter tries to consume 5, 6 as many calories as he typically did before he began his diet. If he typically consumed 2,400 calories per day, how many calories per day should he consume while on the diet? In other words, we want to compute 5, 6 of, and of is multiplication, 2,400. Instead of multiplying 5 times 2,400, it'd be more efficient to divide 6 into 24 4 times, and then carry 2 zeros. So we have 5 times 4, and then add on 2 zeros. So that's going to be 20, add on 2 zeros, so 2,000 calories. Number 3, describe in words. 2 times an unknown number x is 3 more than 5. So a common translation is twice an unknown number x is equal to 3 more than 5. May not use greater than because is greater than is the inequality symbol. Number 4, write using exponential notation and then evaluate. So we have 4 factors of 10 forming this product. So this is a base of 10 with an exponent of 4. A base of 2 repeats 3 times, so cubed, minus negative 3 to the first power times negative 3 squared. That's the total of 3 factors of negative 3. So 10 to the fourth power is a 1 followed by 4 zeros. 2 times 2 times 2 is 8. Board of Operations says do the exponent before subtraction. So that's negative 27 equals 10,008 plus 27 is 10,035. Number 5 is the definition of absolute value, which is said to be defined in 2 pieces, or it's piecewise defined. First piece is if the number inside, called the argument, is a positive number or 0, then the absolute value of the number is itself. If the number is positive or 0. In other words, if the number is non-negative. Otherwise, if the argument or number inside is a negative number, then the absolute value is the opposite of the negative number if x is less than 0. So again, we say this is a piecewise defined expression, defined piecewise in 2 pieces. Number 6, evaluate the absolute value expression if the values of the variables are -2 and -3. So we'll substitute -2 plus -3, the sum and absolute value, minus absolute value of -2, subtract, in parentheses, a -3, is the absolute value of -5 minus the absolute value of. Now minus a negative becomes add +3, so the sum is 1. The absolute value of -5 is its opposite, which is 5, minus 1, final answer is 4. Number 7, use the formula distance equals 5/10 times g times t squared, where d is the distance, g is acceleration due to gravity, t is time of a falling object. Use g as the gravitational force, 32 feet per second squared. An object is dropped from a height of 500 feet above the ground. How far has the object fallen after 5 seconds? So the distance fallen is 5/10 times acceleration due to gravity, 32 feet per second squared, times 5 seconds squared. So 0.5, or 1/2 of 32. We group those factors, that'll be 16 times 25. So divide and cancel, 2 and a 32 is 16 times 25. And then you can use a calculator to check your math, check your arithmetic. And units are always important. So the distance fallen is 400, and distance in this case is measured in feet.